When we look at the percent of total use of nitrogen-based fertilizers in the US, as we described in the previous video, top three are anhydrous ammonia, urea, and urea ammonium nitrate, a gas, a solid, and a liquid. And there's all advantages and disadvantages to each one of these three. By and large, they are used across the US, 44%, 21%, 16%. These are relatively recent numbers. So let's talk about each one individually. And first, let's start with anhydrous ammonia. So anhydrous ammonia is actually a very nice nitrogen fertilizer because it contains 82% nitrogen, the highest of all nitrogen fertilizers on the market today. In fact, you can't get any higher than this. Properties of anhydrous ammonia. It's the first product created from the Haber-Bosch process. The Haber-Bosch process, when you take atmospheric nitrogen and hydrogen gas under intense temperature and pressure plus a catalyst, creates ammonia, the gas that is anhydrous ammonia that is used in this picture that you see on the bottom of the slide. It's a gas. It comes in the tank. Maybe some of you have seen this, and it's typically sliced into the soil. And I'll show you some pictures. It has the highest analysis of all nitrogen fertilizers at 82% nitrogen, and thus it's the cheapest per pound of nitrogen. But it has some drawbacks as well. We'll talk about those. So it's a gas at atmospheric temperature and pressure. So when a producer purchases anhydrous ammonia, it's cooled or it's pressurized to form a liquid inside these tanks. And once the anhydrous ammonia is pumped out of the tank and sliced into the ground, it immediately becomes a gas. It requires some extreme care when handling. If there is a major leak out of the back of this tank and a producer comes out of the tractor and goes back, he or she can walk into a gas of ammonia and actually pass out and or be killed. These tanks are pressurized, so there's risk of explosion. Doesn't happen often, but it can happen. And if you apply it in too great of concentrations, the ammonia can kill plants. Although this is being knifed into a field that looks like it was terminated or it's in a perennial plant or grass species. Anyway, anhydrous ammonia. Anhydrous ammonia, when you purchase this, you typically go to some place like a co-op, and they all have tanks of anhydrous ammonia where you can pump the liquid phase from one tank to the next and then bring it back to the field. This is what happens, and it's impossible for me to show you an actual video of slicing the gas into the soil because you can't see the gas, but this is how this works. Typically, we drop an implement with a knife like you see here in this implement here. Sometimes it's a V-shaped knife. The tubes that are coming down on the bottom of this red V shape deliver the gas to the soil, and there would be tubes that deliver the gas to the soil on this implement as well. There's a tube in this drawing that comes down and releases the gas into the soil. You always want to knife this gas, anhydrous ammonia, into the soil. If the implement is bouncing across the soil surface, where do you think the gas is going to go? And there goes your money. So you want to knife this into the ground. You can do this pre-plant, you can do this in season or in row or in the row, inter-row, like you see in this picture here of corn. And this is the reaction that occurs in soil. The ammonia gas will react with water to form ammonium, which can be used by plants, and hydroxide. So this temporarily raises the pH of the soil, and that can be detrimental to young plants or new seedlings. When a plant's fully established, like this corn here, it likely isn't detrimental. We're going to talk, I think we're going to talk about this in a subsequent slide. So let's talk about loss pathways. The major loss pathway for anhydrous ammonia is volatilization, right? So if you have the implement in this picture, instead of being in the soil, if it's bouncing across the soil surface, it is immediately lost. If the implement is only at a shallow depth, there's a greater chance of volatilization. And after you apply this and the anhydrous ammonia is converted to ammonium, if the pH is above 7, there is a chance that you might lose this as volatilization, all right? Of course, if you don't lose it, if you think back to the nitrogen cycle, there is always a potential for further leaching or denitrification following nitrification in soils. So how do we retain the nitrogen from anhydrous ammonia in soils? The retention of ammonia in soils depends on a number of factors. Soil moisture. The retention increases up to field capacity. We need some moisture in the field for ammonia gas to react with to form ammonium plus hydroxide. And it increases up to field capacity. If the soil is fully saturated, first of all, you probably wouldn't be driving out in a field if it was fully saturated. But by some means, if you were, and you knifed anhydrous ammonia gas into a soil that's fully saturated, where is the gas going to go? It's going to bubble out of the soil and go to the atmosphere, and it's lost. And there goes your money. Clay content increases of retention are simply due to increased CEC and the smaller pore sizes, right? So if you have a heavier textured soil and you're knifing anhydrous ammonia in, the path from injection point to the soil surface is more tortuous to the soil surface in a clay-y textured soil versus a sandy textured soil. And of course, more clay, typically more CEC for retention of ammonium. Organic matter content also is important. The greater the organic matter content, the greater the retention due to pH-dependent charge. And of course, the depth of injection. The deeper the depth, the greater the retention, because there's more soil that the anhydrous ammonia will, quote, see as compared to injecting at a shallower depth. So there's some applications and considerations with respect to soil reactions and the use of anhydrous ammonia. And some of the advantages of this product, it's high analysis, 82% nitrogen. It's cheap. It's the cheapest in terms of per pound of nitrogen, and it can be definitely applied with many field operations. But there's some disadvantages. Some of the disadvantages are that it's a safety hazard. It can irritate your eyes, your lungs, your skin. It actually, if the tank is leaking to a great extent, and you walk back and walk into a cloud of ammonia gas, you could die. You could pass out. I've heard of producers passing out, not many, but one or two producers passing out in a field because they've walked into the cloud of ammonia, which is really scary. This product must be subsurface applied, unlike the other fertilizers we're going to discuss in this unit. Ammonia is toxic. It can burn seeds. It can burn seedlings at great concentrations. It causes a drastic change in pH, even though it's temporary, and it can sterilize the soil around the injection point for maybe 2 weeks, 3 weeks. So this graph shows you what happens. And the reaction, in this case, it's drawn from right to left. When we inject ammonia, it reacts with water and forms ammonium, and it generates hydroxide or hydroxyls. This raises the pH. And so often when you inject anhydrous ammonia, if you follow the pH of the injection point over time, the pH could go from something like about 6.5, it could go up to almost 9. And then, of course, it tapers off as the buffering reactions within soils take over to bring the soil back to a pH that's very similar to where you started. So you need to be careful with this. And so this is what is typically recommended. When you use anhydrous ammonia as a nitrogen fertilizer, you should wait approximately 7 to 10 days after application before you plant. And we recommend that so the plant, the seed or the new seedling that's emerging is not damaged by ammonia toxicity.